what we did was we talked about the DC motor. All right, so the DC motor with that guy, we talked about that with a variable frequency drive, or variable speed drive, I should say. So the example with the DC motor, right? We basically, you had that on the last homework. You've got that on the last problem of this homework. Looks like that. Very similar to the synchronous machine model, right? Basically just a source with a resistor, and then I hook it up to some source, right? So what we basically did was we said, all right, there is in here some sort of a DC-DC converter. And sometimes we draw a DC-DC converter like that. And then we said, if we're controlling the speed, I have that type of a system. If I'm controlling the speed, then I vary the output of that box that I drew there. That box is a DC-DC converter. Okay. So for the basic DC-DC converter type that we dealt with, I talked about the buck converter. I don't care about the full voltage coming out of that thing. I cared about what its average voltage was. And if I built the thing right, the average voltage and the full voltage are about the same. So if I say built it right, so what's inside that box? That DC-DC converter box, right? That's what this thing is, DC-DC converter. What's inside there? Switches, yeah. So basically I go from DC to AC, right? And then I have what after that? Low pass filter, and I should get what at the output is just the average value of that AC waveform I created, which was D times Vn. All right, and what's D called? Yeah, the duty cycle or duty ratio, right? And what values can D take? 0 to 1, okay? 0 to 1. Now, what we talked about the other day is if I have an induction motor, then effectively what I have is a three-phase setup. And I'm not going to talk about the full box. What I talked about the other day is basically this is what you would really have. If I had this whole thing is what would be for an AC motor, a variable frequency, they're VFD, variable frequency drive, VSD, or sometimes you see ASD, adjustable speed drive, and AFD. I've seen all three of those things, or all four of those things in the past. So it's three-phase input on the left, and it's three-phase output on the right, and there would have to be some sort of a capacitor there. We call that the DC link between the two of them. All right. So the first, what kind of circuit is this? Rectifier. Yeah, it's a three-phase rectifier. Has at least 6 diodes. If it's three-phase, could have 12 diodes. We don't need to get into the details of that. That other thing right there that goes from DC to AC is an inverter. Basically, what it amounts to is a three-phase version of a buck converter, right? Without getting too specific about that. Now, the voltages that it creates, if I look at here on this side of the machine, VAS, that voltage is basically the average value of some crazy-looking switching waveform. And effectively, it has 2 elements that can be adjusted, okay? Usually what we say is if this is the DC link voltage, I'll call that Vn, that voltage there. Usually what it has is some amplitude. I'll write it this way. Yeah, I'll write it this way. M times V in times cosine omega t. I'll write it that way. All right, that M is related to the duty ratio, and that M value is between 0 and 1. M stands for modulation. All right. So I briefly kind of described last time. All right. If I want to drive this thing properly as a motor, what we have to do is we have to generate a three-phase set of voltages. All right, and we generate them just like the buck converter does, and we vary the amplitude of it and the frequency of it. Now, why did we vary the frequency of this thing? So the example that I gave last time was I said, all right, let's say I'm hooked up to a pump, right? If I'm hooked up to a pump, what's the torque look like on a pump? So the load torque on a pump, what's that going to look like as a function of speed? Yeah, it's beta times omega m squared. In other words, there's very little friction in the water at low speed, but it goes up very quickly at higher speeds. Okay, that's what that means. And so that also tells me that if I really wanted to be able to control the power in the system pretty effectively, then what I want to do is to try to adjust the speed of the machine, right? So how do I adjust the speed of the machine? If I'm operating a pump and the pump needs to operate at a particular flow rate, right? How do I adjust the speed? How could I use this device here to adjust the speed? You change the frequency of the voltage that you apply, right? Because basically what we said is there's a very narrow range of frequencies that this motor will actually operate with, right? Now we're going to look at a example here as we go, but basically this, I'll jump ahead for a second. This is sort of this guy right here. This is the electrical torque of the machine, right? It's got a big curve, which, starts at 0 RPM and goes up to the synchronous speed. But we said that generally speaking, he operates in a pretty narrow range. So if I want to actually vary his speed, what I have to do is I have to vary this point right here, right? I have to vary what the synchronous speed is. And how do I vary what the synchronous speed is? What do I have to vary to control that? What's making this guy spin at 1800 RPM? What controls that?
The grid frequency.
The grid frequency, right? So I basically have to change the frequency of the grid. And that's essentially what this box here is doing, is it's changing the frequency of the applied voltage. Okay, so we're gonna go through an example to kind of think that through. Okay. All right, so let's do something like what's in problem 1 and problem 2 on the homework. Okay, so basically with this, all right, this is our basic induction machine circuit right here. All right, I've shown I2 going 2 different directions. I don't want that, right? That comes out of how I derived that circuit model. So let's just show I2 going that way like that. And I've got my key relationships there: the air gap power, the mechanical power, and the torque electrical. Those are the things that I need to understand to be able to figure out how this thing operates. These are electromechanical devices, so I have to look at the torque speed relationship to know how this thing's going to function. Okay. All right. So let's figure out how we're going to get this thing to operate. All right. And in particular, I want to look at a machine that has these parameters right here. And this is ultimately a 25 horsepower motor. All right. Again, the motor ratings are always in the US in horsepower. In Europe, you'll see them in kW. In the US, it's always in horsepower. All right. When I look at this, I've got a 4-pole machine. It's 460 volts. And then I have the parameters that are given right there. All right. So what I want to do is I want to figure out how this thing is going to operate. And I'm going to run that same kind of simulation model that you have in the homework. And I want to run this guy a couple of different ways. So if he's 25 horsepower, I want to start out with basically, I want to put a load on this thing that is, so I'm going to put a 25 horsepower load. And let me do it this way. I do this. So this guy was observed. Let's just say the load on this guy is equal to 101.0959 Newton meters. Do it that way. Okay. That's the load torque on this guy. All right. Where is he going to be operating? What speed? If I ask you, okay, that's the load, and this is in problem 1, it's like that. You've got a particular load torque that's on the machine, and you're asked, to figure out, what the currents are going to be and all that sort of stuff. If I ask you where this machine is operating, and I say that's the load torque, where do I start with that? What's the first thing you have to figure out? So let's say, and what I mean by that is, all right, let's say I want to figure out what the currents are going to be and all that kind of stuff. I want to figure out what the input power is going to be. Musa, you're off the clock. I'm taking you off. Where am I gonna, how do I figure out where I start with operation? What's the first step?
Well, we know what it's a full port generator, so it's going at 100 RPMs.
That's what its synchronous speed is. Which is a good point. It's gonna be a little bit less than that, right? That's right. So let's capture that. I do ask you that in that particular problem. I ask you what's the synchronous speed going to be? The synchronous speed is basically omega divided by p over 2, which is going to end up being in RPM 1800 RPM. So that is a key point. And Dan's right. My mechanical speed is going to be a little bit less than that. But to do anything, I have to know exactly what a little bit less than is, right? So how would I figure out what a little bit less than is? What's step one? Convert the 25 horsepower to what? Well, all right. So horsepower is power, right? So that would have to be into watts. That I would. But the important thing about this is what I'm telling you, and this is why I want to go over this example. So when I say this is a 25 horsepower motor, that means that's what its rated condition is. All right. And if you like what I showed you the other day, I showed you the nameplate on the motor, right? I think I showed you a 100 horsepower motor nameplate. That's to say that's what it's rated for. So where it should operate is basically between 0 and 100 horsepower. Yeah. And its speed varies somewhere between, full speed and whatever speed it has at 100 horsepower. So that's the same thing going on with this guy, right? So his full power range would be from 0 to 25 horsepower. So to figure out what speed he's going to operate at, well, so I'm just telling you this guy has a fixed load, right? To be able, and so let me say it this way. To be able to do anything with this circuit here, what do I need to know? To do anything with that circuit, I need to know the slip. If I need to know the slip, what do I need to know? You need to know what omega m. You need to know what speed he's going to operate at, right? So the other kind of key relationship that I probably need here, right, is that the slip is equal to the synchronous speed minus omega m divided by the synchronous speed. Okay. So I need to know what the slip's going to be. So how would I figure out? Well, I know what this is. I know what omega s is. I need to figure out what omega m is going to be. How do I figure out what omega m is going to be if I know this is the load? I don't know what speed though. So there's no way for me to get a watts. So, okay, this is so 25 horsepower is a rating. I don't know if it's operating at that rating. That's what it's rated to operate at, right? And that's an important point. Like what I'm trying to say is a motor has a rating, but it doesn't necessarily operate it as rated. Where does it operate? It operates at wherever Mother Nature says it's going to operate to drive the load. So that load requires 101.0959 Newton meters. That guy is going to do what? Well, you basically apply voltages to it. He's going to spin up. He's going to get to some speed, right? How do I figure out what speed he's going to get to? Well, Newton's law tells us that J d omega m by dt, which says what? What does that mean in words? What is that equal to? Yeah, the net torque on this thing. So how do we write this net torque relationship always? Electrical minus mechanical in this case. Why electrical minus mechanical? I am talking to you. You made a smart statement there. It's good. I'm proud of you.
Your favorite formula?
It's my favorite formula. Well, it's a good question. It might be. I don't know. Why is it electrical minus mechanical and not mechanical minus electrical? It's a motor. Yeah, it's a motor, right? So I'm saying it's requiring electrical energy to move in a positive direction. If I have a generator, it requires mechanical speed, mechanical power to operate in a positive direction. Okay. It says electrical energy accelerates it. Mechanical energy slows it down. All right, it's basically what that says. All right. If I get to steady state, what is true about the speed? Speed's constant. So in steady state, right? Steady state, I basically have that tau E equals tau M. Okay. All right. So has that helped me to figure out what omega M is? Not really. Right. At least we know what we're trying to find. Right. How do I figure out what omega M is going to be? Now you did this on the last homework. Get the torque speed curve for it and figure out where the low torque and the mechanical, so that where the mechanical torque and the electrical torque are equal to each other. What is the speed at which that happens? Okay, so basically what we do is I want to be able to generate two curves. Right, here's omega. This point right here, let me take it all the way to, here's omega M. Okay. This is, what point is that right there? Omega S. This is my synchronous speed. And my 101, let's say this is my tau M, that 101, whatever number. This is my tau electrical. Wherever they meet, that is my omega M, I don't know what to call it, omega M op. That is the speed at which I'm operating. Okay. The machine, where does the machine start? This is one thing I want, because I do ask some questions about this in the homework. What speed does the machine start at? 0, right? That makes sense. It starts at 0. The field appears in the machine. That induces currents. This guy starts to spin up. And he spins up to the point where these two things intersect. All right. So how do I find that intersection point? Well, I have to generate the torque speed curve. And I have to figure out where does it equal to that value. Okay, so how do I approach that problem then? How do I approach the problem of finding this point of intersection? What do I have to do? I do, and that, right. That formula for torque electrical is here. So it's the mechanical power divided by omega M. It ends up being in the form of the slip. Okay. All right, so it becomes this guy right here. So torque electrical. All right, torque electrical is 3 over omega times P over 2 magnitude of I2 squared times R2 over S, like that. Okay, that is our basic torque curve. All right. Well, yeah, that's the other. I should be careful. This is omega S. I think, yeah, be clear. That is the synchronous speed right there. All right. All right. That right there is our torque relationship. So what do I have to do to figure that out? Find I2. Right. Find I2. So how do I find I2? All right, again. First find IAS and do current division. Okay. Now, if I'm going to approach that problem, again, the simplest way, you have to generate a graph in MATLAB. One question people asked me on the last homework, there is no easy, I mean, there probably, well, there is a way to do a solution for this, right? To do a solver or something like that. It's obviously not the kind of thing that I would ask you to do on a test. All right. On a test, most likely what I would tell you is, okay, it's operating at a particular slip or something like that, right? And then you would go from there, all right? But I'm asking you to go that first step to find out, okay, where is it going to be operating? All right, so I would have to go in here and I would have to figure out what IAS is, right? IAS would be VAS divided by whatever Z is. So what's the Z here? Yes, that sounds about right. Yeah, that Z, you guys should be able to follow him with there. R1 plus JX1. All right, that's an important thing to remember. I saw a lot of people not putting the J, right? X is a reactance. It's not, this X is not an impedance, right? It's the imaginary part of an impedance, right? So I put that J on there. And then I have basically JXM in parallel with JX2 plus R2 over S. All right, that's my approach. Then I go through the current division to figure out what I2 is going to be. All right, once I know I2, I basically go through that formula right there to try to generate it. Okay. All right, that's the basic approach that we follow. So let me, what I want to do is show how do I approach that, because I did that here. Okay. All right, so here's my code. So first of all, I almost always, the rating on a machine is almost always given to you in line to line, but that is a single phase circuit, right? So the first thing I always do is convert that to a line to neutral voltage. Now, in the assignment, I think even in this homework, I gave you basically an S vector, right? So that you can generate from there and it can check stuff. You could do whatever you, in fact, in this particular case, I think maybe in problem 1, the first part of it, I ask you to show me the torque speed curve or to enter it. But I don't know that I ask for that in every problem, right? But I give you this S vector here. All right, and then you can look at how I generated that code to be able to put that in there, right, with those values. And I tried to walk through this probably a little bit more step by step than what I was seeing from some of you guys. My suggestion to you would be to try to do it step by step so that you don't make a mistake in terms of how you do it, right? Ultimately, what I have here is I finally get down to the torque relationship there. All right, so that's my overall torque relationship there. Okay, and then I ultimately plot here all of the relationships that I care about. So what I plotted, and notice how what I did, I created a vector called RPM, which is my speed vector, and I based that off of the S vector. And what I'm plotting is a couple of different things. And what I want to do is I want to pull up the curve here. All right. And let's take a quick look at how do I find the operating point. So I'm going to set my zoom here. I'm going to zoom out on this guy. Okay. All right. So I've got a bunch of different curves that I drew on there. What curves are which? Which one's the torque speed curve? Yeah, I guess that's sort of orange. I don't know. This one here is my torque speed curve. All right. Torque speed curve typically kind of peaks up a little bit as I get closer to synchronous speed. Yours is going to look a little bit different than this one in the homework. They tend to look a little bit different based on the design of the machine. Which one's the current and which one's the power? What's that? Current should be what? Current's blue. And power is this one here. Well, first of all, why is the power is the one to me that should be obvious if I look at it. If I look at the two ends of it, what's true about the power at the two ends at 0 speed and at full speed? 0. Why would it be 0 at both ends? What's that?
It's like at 0 isn't power.
Well, how much at 0 speed, how much power can I possibly have? 0, because I'm not moving, right? Omega is 0. If omega is 0, it doesn't matter what the torque is, there's no power. At full speed, I've got speed, but I have no what? Well, yeah, I've got no power, right? So turns out I have no I2 current, but I do have current going into the machine. But there's no load. So we should address that point, right? If I look at this one here is the current versus speed curve. I got a lot of current here at 0 speed. And I don't have zero current at full speed, right? You guys may not be able to see that too well, but looking out here, it probably ends up being about 10 amps. That's IAS. Yeah, what I've shown here is the input current to the machine. If I looked at I2, I would see nothing. Because why? Why would there be nothing at full speed? What's the slip equal to at zero speed? Yeah, at zero or at full speed, the slip is zero, right? So if I'm looking at my circuit, if this thing gets all the way up to, right? If I get all the way up to full speed, so omega S equal to omega M, slip has to be equal to zero, and R2 over S goes to infinity. Now, in problem 1, I do ask you to run the machine with zero load torque. Okay. If you try to calculate what is I2 going to be with S equal to 0, you're not going to get an answer from MATLAB. Right? Why not? Because it's going to say that impedance out there is infinite. Right? So it's going to say not a number of values. However, you can be smart about this. There's still current. If I'm actually talking about the situation where S equals 0, so R2 over S is infinite, what's the impedance that I'm looking at? Well, how do I simplify that circuit? If that's the situation, if I have R2 over S equal to infinity, right? So how do I simplify this circuit in that case? It becomes an open circuit, right? So I get VAS, I get R1, right? I get XM, X1. I guess X2 is over here, right? But R2 over S is not there. Okay. So if I'm talking about trying to figure out what IAS equals in that particular case, right? If this is IAS, what is it going to be? It's going to be VAS divided by R1 plus JX1 plus JXM. Like that. Okay. You're going to have to put that in by hand. If you try to go into MATLAB, you better put that in by hand, right? Because it's not going to like that if you leave the R2 over S in there and S is 0. Okay. It'll probably run, but you're going to get not a number as the answer. Yeah. All right. So that's that. But I will go back to where I was going with this, where I had the situation where I just want to draw the torque speed curve, and I want to figure out where this guy's going to sort of intersect. Okay. So how would I figure that out once I've got this result here? Yeah, I see where they intersect. So in this particular case, what I do is I usually try to zoom in. What I did, and I think in problem 1, I actually put into the solution and commented out the formula that I used, all right, for making the plot. The comment that I included basically looks like this. All right, if we dissect this, I basically have, and let me expand this out. So in figure 1 here, what this is saying is I'm doing RPM. So I'm plotting X. So it's always X, Y, X, Y, X, Y. So I put a couple of different things on here, right? Basically, I put the current going into the machine, the torque produced by the machine, the mechanical power. This is my load torque right here. And what am I doing here with this? This is just a MATLAB question. What am I doing here? I'm making a vector of 1s that's the size of RPM. So basically making just a constant that's going straight across. That way I can kind of easily have something to look for, right? So I plotted a straight line. And again, I left this commented out in the solution for problem 1. So you guys could use something like that if you wanted to. So if I look at the torque speed curve, right, what I do here is I just kind of zoom in on this point here. All right, and then what I do is I go to this data tip thing, and I'll click in a particular point on this curve, right? And then what I typically do is I can just use the arrow button here and kind of see where do they intersect. So looking at this, you're not going to get it exact, but there's enough room for you to find the right location. So if I'm looking at enough rounding room. So this says 1731.5. It's just below. And at 1731.41, it's just above. So it's probably about 1731. That's close enough, right? So I think this guy's going to operate. It's saying at about 1731 RPM, right? That's what it's telling me. So once I know that, what can I use that to do? Well, if you look at the problem statement that I give you in the homework, it's okay, find me the input current, find me find me the input current at the operating point, find me the power at the operating point, find me the reactive power at the operating point. So I know the operating point now, right? Now the operating point is basically 1731 RPM. So what do I do with that? Once I know it's 1731 RPM, how do I take that into account in my analysis here? I could find the slip, right? We know that the slip is that relationship. So basically what I'm going to do is I'm going to say, okay, well, once I made that graph, I have that my slip is 17. So it's omega S 1800 minus 1731 divided by 1800. And I can calculate what that is. Okay. So what I did pretty much in my code is just to, I mean, at this point, you can plug this into your calculator however you want, right? If you're more comfortable with that, go for it, right? I'm fine with that. You're not gonna be able to do the torque speed curve that way, right? You're gonna have to generate that. But you could then take this and you can then plug that into the formulas for everything else, right? To figure it out. So let's take a look. So what I did was I simulated that. So this is this particular motor. It's the same setup that we did in problem 1 and 2, right? So what I've got is I put that particular machine setup in there. Those are the parameters. I ran this thing. All right. So I want to figure out if it's actually operating at the right point. So what I've got here is all of the green things are oscilloscopes. So I can take a look to see where this guy's actually operating. All right. So where should I start? I should probably start with the speed, right? Because that's what we just found. All right. So let me go to the speed. So this one here is the speed. All right. And this is the speed graph. And I've got this guy set up, all right, to tell me the speed. And it's telling me that it's operating at according to this, can you guys read that? It's 1732 RPM. So it's about what we were expecting it to be. Okay. Maybe if I just turn down the lights for one up, one down. Is that okay? All right. I'd like to meet the electrician who did that. This guy should be running at about 1732 RPM. All right. So again, still not sure if you can really see that. It's very clear on this screen, but it's not ever on that one. Now, that is sort of the way I would expect it to operate. What should the torque be? Right. So I also have here the electrical torque. All right. That's what this one is. What should the torque be in steady state? Equal to the mechanical torque, which we said was about 101 or whatever, right? So let's take a look at what it is. All right, now that's what it is. Boy, that looks weird, doesn't it? What the heck is going on there? It's so, and which ripple effect are you talking? Because yeah, you could be talking about that probably. Yeah, that part's the part that probably caught your attention. Yeah, but there is a ripple on out there in this particular case in steady state as well. It looks like it got to something steady, but it's kind of fat there, right? If I zoomed in on that fatness, right, there's going to be some ripple around that. So this is a function of the startup process of the machine. All right. In most machines, in reality, you see some of this, but not that much of this. All right. So that's probably distracting a little bit when you're looking at it. but let's kind of ignore it for a second. What it looks like is I have ripple that I get to in steady state, right? But I still get to rippling around some kind of a constant point, right? And that constant point should be about 100 and some RPM or 100 and some Newton meters. So let's zoom in on that. I wish it didn't default to this black background. You guys would probably be able to see it much better. All right. If I look at where this guy kind of gets to, sort of the center point here, again, so weird, the lights. That is operating somewhere, man, you really can't see that very well at all. This is about, this line right here is what, 98? Yeah, and the one above it there is 100. So this guy's operating, like the center point there is about 101, right? Just sort of about where we would expect it to be, right? Why does it have this ripple? Right? I thought it should be constant. Any idea why it would have that look? The reason why it's rippling is all of this stuff down here is I've put in that variable frequency drive. What's inside the variable frequency drive? Am I just applying a straight cosine to this thing? No, right? What I'm applying to it is a waveform. This is the voltage that I apply, all right? If I zoom in on this voltage is basically a square wave of the varying duty ratio, all right? So if I zoom in on that, it is an ugly looking thing, right? What does that mean, right? This guy has a fundamental frequency. The fundamental frequency of it's 60 hertz, okay? But it's got higher order harmonics as well, right? So if I were to look at if this is what the voltage looked like, what do you think the current looks like? What should the current look like? What was the basic principle for this? This guy's operating using pulse width modulation, a more complicated pulse width modulation that we're not going to talk about in detail. But in this particular case, pulse width modulation's going on. What was the key thing that allowed pulse width modulation to be used? Low pass filtering in my load. My load needed some kind of low pass filtering characteristic. So if I look at the induction machine, right? Right. So if I look at my induction machine here, if this is my basic, where did I put my marker? Is it? Yeah, true. Yeah, wife. Yeah. Yeah, that makes perfect sense. Somehow, if I were to basically say to you, all right, well, give me the Thevenin equivalent impedance looking into that thing, right? Reduce that down to something. If you were to reduce that down, what would the combined impedance be? At least approximately. There'd be two things in there, wouldn't it? What two things would be, if I said to you, what is that Thevenin equivalent impedance? And you could give me some numbers for it or whatever, but what would I end up with if I simplified that thing down to one equivalent impedance? An inductor and a resistor. Right? And let's say this is IAS and this is VAS here. If I were to try to figure out VAS, so there's a transfer function here, VAS as my input, IAS is my output. What is that transfer function? So V is the input, I is the output. What's the relationship between those two things? What's V over I? Well, it's a 1 over Z, right? So what's 1 over Z? This guy's going to end up being 1 over J omega L plus R. Like that. Is that a low pass behavior? Is that a low pass filter? In other words, so what I'm saying is that transfer, you guys should understand transfer functions, right? I have a voltage going in, I have a current coming out. That's the output of this system, right? That's a low pass transfer function, isn't it? It is. Yeah. So this guy is basically he's got his low pass filter. So in other words, I put an ugly voltage in, but my current should be smooth, right? If I've set this guy up right. And if I look at that, right, this is the voltage I'm putting in, got a lot of high frequency stuff to it. If I look at the current, where's the, all right. All right, so this guy has two different things going on. The top part is, well, here's one current, there's another current. There's two currents there. Which current is where, do you think? One of them is the rotor, and one of them is the stator. Which one of them do you think is the rotor? The top one would be the rotor. Why? Well, but just looking at if I look at the frequency of this thing, the frequencies are very different, right? The frequency of this guy, which one has a higher frequency? Let's just look at the steady state portion down here. Which one has a higher frequency? The bottom, right? What frequency is the bottom? If it's the stator, what frequency does it have to? 60 hertz, right? What about the top one? Much lower frequency. Why is it lower in frequency? What's true about the real rotor?
It's a motor?
It's a motor. It's an induction motor here. So what was true about the frequency of the current on the rotor? It was lower, right? Because the whole idea was that when the rotor is operating, or when the machine's operating in steady state, the rotor is spinning a little bit below synchronous speed, which means the rotor is moving a little bit slower than that field inside the air gap, which is inducing a current in the rotor, right? And that's why that current is a very low frequency. What would the frequency of that current be if I was at synchronous speed? 0, right? And there would actually be none, right? Right, so this guy is at a much lower frequency, and you can figure that out. Basically, what's the difference between 60 hertz and P/2 times the mechanical speed? In other words, if I said what's the frequency of that, it ends up being right. The frequency of that current in the rotor ends up being omega minus P/2 times omega m, right? This is what we call the electrical frequency of that thing. Okay, so we've got that all worked out. All right, with those relationships, we can those things can make sense to us. But I want to understand why the curves look the way that they do, right? If I look at the current here, let's contrast the current to the voltage. So let's just look at this one here for a second, right? And let's just look at it at a high level, right? What I'm looking at here, it's a 60 hertz current. If I zoom in on it, you'll see a 60 hertz look. Why is it bigger and then smaller? Yeah, that's right. The torque starts high and then comes down, and if the torque is high, what's true about the currents? Currents have to be high, right? Why do the currents end up being high? Well, so there's the term this is called the inrush period, but I should be able to justify this from the circuit. Okay. One thing that you see sometimes on motors is a parameter called the locked rotor current. All right. What do you think that means, locked rotor current? What do you think it means by locked? It's the frequency of it's 0, right? Where it's locked is where it's starting, right? And if I were to look at this time period right here and align this with the speed, so this is the current, and if I show on top of this the speed during that time period where the current was high, what's the speed doing? Increasing, right? So it's basically going through this period where it's accelerating. So if I were to look at the slip, right? I'm looking at the speed, but if I were to convert that over to the slip, what's the slip doing? Well, what's the slip here? Is it high or low? It's at 0 speed, it's at 1, so it's a high number. By the time I get up to the end, it's basically close to 0. Right? So what's happening to that R over S? What's R over S doing as I go from 0 speed to full speed? Well, yeah, R over S is basically going from a short circuit type of condition to an open circuit type of condition, right? So the circuit model is totally changing in that time period, right? So if I look at the circuit model, let's take a look at it for a second. Looking at the circuit model, right? So we've got R, X, so this is R1, X1, this is XM, this is X2, and this is R2 over S. All right, so if I'm at full speed means S equals 0, and if I'm at no speed, what I'll call locked rotor condition, right? S equals 1. Okay. Now, at full speed, we already said this guy's going to look like this. Okay. At no speed, what's this guy going to be? How would I simplify that circuit? Yeah, I got a short circuit. I've sort of like a short circuit, I guess. The over S becomes 1. It's not really a short circuit, but this guy is just R2 now. X2, XM, X1, and R1 like that. Okay. Now, in this case, R2 over S is equal to infinity, right? R2 over S is infinity. In this case, R2 over S is R2, all right? So they've gotten to be pretty different. All right. Thinking through what's going on here, the current, and just intuitively, the current here is going to be much higher. I'm sorry, the impedance here is going to be much higher. The current's going to be much lower here than it is there. Now, why? It depends on the values of the parameters. So let's just look at the values here, right? So XM, just copy these over to that slide. Okay. Let's think this through. Okay. All right. So there's those parameters. Okay. And let's compare them real quick. Which parameter is the highest? Which impedance parameter is the highest? XM. Why is XM the highest? Like when we saw transformers, this magnetizing inductance was always the highest, right? It is the primary path that our field's going through. That parameter is always the biggest. Why are my resistances? They're both small. They're both less than an ohm, I think. Yeah, they're both less than an ohm. Why are my resistances so small? I want those to be small, right? In fact, I kind of like them to be 0, right? Why do I want them to be 0? Because they represent losses, right? So they're not a good thing. So I typically want those to be small, right? I want my leakages to be small too, because heck, they're leakages, right? They represent flux that's ultimately not going into sort of usefulness to me, right? So let's think about the conditions here, right? If I look at R2 and X2, those values they're in series with each other, but they're much smaller than XM, right? So if I talked about the impedance here, right? The impedance of this guy has in it JXM in parallel with R2 plus JX2. Now I realize this is complex. I got to talk in terms of magnitudes, but you should be able to look at that and say, which one of those impedances is going to have a bigger magnitude, XM or R2 plus JX2? XM, right? So where is most of the current going to be flowing in this condition? R2 plus X2, right? So in that condition, basically it's like XM. Again, I'm just going to approximate it this way and say it looks like that, right? Approximately so. And in this particular case, my total impedance is actually quite high, right? My total impedance here is going to be at least 26. Whereas my total impedance here is going to be what? It's going to be much, much smaller, right? Because that 26, which is the big one's not even there, right? So the current is going to be much higher in this case, right, than it will be in this one. All right, that should hopefully be clear to you. And in fact, just intuitively, if I just ask myself, and let's look at this guy here for a second, at full speed, I can look at this thing right now and say, here's IAS. I should be able to figure out what's my P going to be. What's my P going to be? If I knew what IAS was, what would my P be in this situation? My power. If I know what IAS is, how can I figure out what the power is going to be? Well, VAS times IAS conjugate, right? What'd you say? Sure. Well, yeah, I mean, the power is going to end up being, because it's three-phase, 3 times the magnitude of I squared times what? Well, and specifically just times the real part of the impedance, right? The X isn't going to contribute anything to that, right? Because it's a P value, right? That is going to be pretty small, right? Why? R1 is pretty small, right? If I look at Q, which one's going to be bigger? Why is Q going to be bigger? Yeah, XM is big. If I look at this condition, usually my power factor is very close to what? 0 or 1? Very close to 0. I will have a very low power factor. This isn't going to be a great power factor, but this is going to be a pretty low power. I mean, this should be almost 0 power factor, right? Because that X value is much bigger than the R value. Okay. So and you will see that that's in the homework that you look at that, right? But all right, looking at this, what's important about this to me is if I go through this, I see the current should be a lot higher at no speed than it is at once I get up close to full speed or my operating condition. And that is exactly what is happening here, right? My current is big. And in fact, if I check the amplitude of that current basically is going to be very close to the lock rotor current, right? Now, how can I figure out what that's going to be? Well, there's a couple of easy ways to figure it out. But if I'm looking at this curve right here, how can I figure out and justify what the current is at low speed? So let's restore this guy. What's the current going to be at low speed? Yeah, I can basically look at what it is at 0, right? And it's going to be pretty close to that. So if I do that here, all right, and I go to this data tip and go to there. Now this one's actually fairly easy just to calculate because I can put in slip equal to 1 and get it pretty easily, right? But I can just drag this guy all the way down there, and it tells me that at 0 speed, the current should be at 144.5 amps. And these were all calculated because I was using phasers with RMS. Okay. So to check that, what I did was, let's see. I gave you guys the time domain waveform, but I also gave you what we often just measure in the real world, which is this curve right here. This is just basically showing me the RMS value of the current over time. So let me kill the lights down here for a second. I'm not sure how well that helps, right? If I look at it, I see the current's really big, and then basically it settles into its final value. This is really it's the amplitude of that thing over time, right? So if I look at what it's doing at 0 speed and pull this guy all the way over here, I don't know why you guys can see that, but it's saying it's about 144.5. All right. And that was exactly what I predicted from here, about 144.5. Okay. All right. Now, one of the things I also ask you is, okay, well, what's the current going to be at the operating condition? Okay. For that, I could zoom in on that particular point and figure that out, right? So how would I do that? If I wanted to, what I could do is I know that it's operating at this speed. So I could drop down to the blue curve and say, what's going on at that particular speed? That's kind of an obnoxious thing to do, I think, right? What I did, and it's probably the kind of thing that you should do, because it's the kind of thing I would do on a test, all right, is if I go to my code here for a second, what I did, for instance, where is it? What I did is I basically defined for myself what I think my operating speed is. Okay, now I know that this operating speed is different, but I basically put in my operating speed. I calculated an S operating. And then effectively what I did was I just copied over all my code to generate the torque speed curve and just called everything in terms of S op. Right. And then I was able to just take the magnitude and everything like that. Right. I would suggest you probably try to do something similar to that. Right. That way you can get a nice number and plug it in. Right. And then to get the power and everything like that, I just calculated my S and get the real and imaginary part of that. Okay. That's probably the way I would recommend trying to approach a problem like that. But if I were to recalculate that, so what did we say it was 1731 is the way that guy should be operating. So if I run this and evaluate that, what it tells me is that my I1 is, so I1 op here is what I've called the operating condition. So I take the absolute value of that. And it says it's operating at, in this case, at for 1731, that this guy should be operating at 29.0602 amps, right? And so if I go to the simulation, that's pretty close to what I have here, 28.81, right? And again, it's a little bit different, probably because my speed's a little bit different, right? Based on the number that I plugged in. All right. So the bottom line is what I see happening is that the current kind of descends down to a lower value. Okay. Now, I want to compare here real quick. Now I know you definitely can't see this. This is about 3 seconds right here. So what it says is it's taken this motor about 3 seconds to start up. All right. What's going to control how long it takes for this machine to start up? Because that is a question that I ask you about a little bit in the homework. What's going to control how long it takes for this machine to start? What's that? How big it is, yeah. So how big it is in the context of how much inertia does it have? Not necessarily how big it is in terms of the rating of the motor, but how big it is in terms of the inertia it has to start up. When you're starting a motor, it's like you're charging a capacitor. When you charge a capacitor, I have a lot of energy. If it's a big capacitor, I have a lot of energy, right? If I charge a 1 farad capacitor and a 1 microfarad capacitor at the same current, it takes a lot longer to charge the 1 microfarad or the 1 farad capacitor than the 1 microfarad. If I have a big fat rotor, right, it takes a long time to charge up a big fat rotor relative to a small rotor. It's just an energy storage device. But it depends on more than just that, right? What controls whose law controls the torque conditions? What controls the torque? What controls the torque speed relationship? Newton's second. Yeah, Newton's second law, right? So Newton's second law is J d omega dt is equal to tau electrical minus tau mechanical, right? So if I look at this, all right, let's go to my curve here. Not that curve. Let me go to the one that I have here. Okay. All right, I go to this curve right here. So it's helpful for me. I have tau electrical and I see tau mechanical on top of each other. Okay. And again, I'm doing this for a constant load torque. In problem 1, you guys have a constant load torque. In problem 2, you have a pump. All right, constant load torque is still pretty common. Constant load torque would be a compressor type of load. All right. You go into a into a plant like a factory or something like that. One of the biggest things is going to be an air compressor. Air compressor would have a pretty flat torque like that. All right. The pump has the torque that goes as beta omega squared. This guy's kind of a constant. All right. I want to look at that for a second because looking at those two curves, that tells me where I'm going to operate in steady state. But I can also use those curves to kind of think about how the motor is going to start, right? How it's going to go through that startup process. So if I look at the torque curve, all right, because I pulled that up as well. And let's reset this guy to the original view. Other than the fact that I got this weird fuzzy stuff going on here. If I factored that out of my brain and I watch what's happening, doesn't the startup period kind of look like the torque speed curve? Right? The torque speed curve is torque on the y-axis, speed on the x-axis. But doesn't this kind of look the same way? Right? What this is saying is that as I get closer to the steady state, the torque that the machine is producing is getting bigger and bigger and bigger and bigger, and then it kind of collapses down. Because what it's doing is over time, right? As I go through startup, it's saying that basically J d omega dt is equal to tau electrical minus tau mechanical. So at time t equal to 0, what's my speed? At time t equal to 0? 0. So basically, I'm operating right here at that particular point in time, right? So my tau electrical is whatever this number is at that time. My tau mechanical is right here. Now, once I apply the voltages at t equal to 0, this is my net torque, right? The difference between those two curves, tau electrical, right? This is tau electrical. This is tau mechanical. The difference between those two curves is what? It's the net torque, right? If the net torque controls what? How fast I accelerate, right? So if I look at this, if I were to sort of analyze how this thing's behaving, right? I have tau e is more than tau m. So what's the speed going to do? Accelerate. It's going to go up, right? So basically, if I looked at it a little bit later in time, I should have moved to some higher speed. And then if I look at it a little bit later in time, I'll move to another higher speed. A little bit later in time, I'll move to another higher speed. And I keep going like that. And what's going to happen is over time, the net torque is going to get bigger. And as the net torque gets bigger, the rate of change of speed should go up, right? And the torque produced by the machine should be going up. And that's exactly what I'm seeing happening, right? The torque produced by the machine kind of is at a level value sort of, and then it's starting to increase and shoot up, right? As it gets to that big part of the torque speed curve. And if I look at it, the speed, right? It starts out kind of slowly increasing. And then it starts to get to a faster increase. Why did it get to a faster increase? Well, because the net torque, which is the difference between those two things, is getting bigger, right? So that means the rate of change of speed is going to get bigger, right? He's going to accelerate faster. So let me ask you this, because I asked this question also in the homework, right? Let's say that this machine was unloaded. If it's unloaded, what's tau mechanical? 0. So if tau mechanical was 0, where is the net torque higher? If tau mechanical is wherever it is right now, or when tau mechanical is 0? When it's 0, the net torque is going to be much bigger. So which condition is the motor going to start faster? With no load or with full load? No load, right? So again, you guys can't see that very well here, but if you look at how long it takes this guy to get to steady state, it's only over about 3 seconds, right? So I did it before class here with 0 torque applied. All right. With 0 torque applied, this one you actually feel a little better. This is 1 second right here. So this guy takes about 0.6, 0.7 seconds to get to full speed because there's a heck of a lot more accelerating torque on that. All right. Now, this gets into a real issue because in this particular case, right, this is a real issue that we worry about with motors here. When that accelerating torque is small, like it is here at startup, that means that the starting time is going to take a while. Okay. In general, and we see this here, right? This guy is operating as we showed. If I look at this curve, at the operating condition, he was pulling about 29 amps. At his full load condition, he was pulling about 145 amps. Or sorry, at locked rotor conditions, it's 145. Where he was operating was like 29. There's a big difference between those two conditions, right? So the problem that you have is if this accelerating torque, the difference between the electrical and the mechanical, if that number is small during the starting period, what's that say about how long it's going to take to start? It's going to take a while. And what's that say about the current? Current's going to be very high for a long time, right? And that's potentially problematic because what happens if I have high currents like that, right? I got a lot of heat getting generated and all that sort of stuff, right? Typically, that current during startup here, right? Typically, that current during startup is about 6 times higher than what it is when it's at its rated condition. All right, that's typically the case. It's about, so in per unit, they'll say it's 600% per unit, right? It's typically about that high. And so you don't want to be in that condition for a long period of time. In fact, you could get into a condition where, let's say tau mechanical was, I don't know, let's say tau mechanical was here. It was a straight line like that. From an operating perspective, that looks fine, right? Because these guys intersect right here, right? But will this machine start? No, because there's more mechanical torque on this machine than it can produce. All right. Now, in theory, this also says that what's the machine going to do? It says it's going to become a generator, right? But that's if I have an air compressor hooked up to this thing, that air compressor is not going to start magically uncompressing air to make the motor move forward, right? It's just going to be stuck there, trying to. You'll hear it. You will hear it go, sort of a grinding sort of sound as it tries to go, because there's a hell of a lot of torque's being generated, but it's not doing anything. It's just stuck there, right? And your current is stuck at a high condition. So this is when you get into motor protection. If you become a protection engineer or whatever, this is a very common thing to think about, because this will be a situation where if I had a large motor, you'd be very concerned about this situation, and you would want to make sure that you didn't allow it to stay in that locked rotor condition for too long. You'd want it to trip off, right? Because something apparently got it stuck. Okay. So you're going to experiment with that, kind of idea a little bit, because it's, so just trying to understand sort of the basic performance of the induction motor, right, and how it kind of operates. Okay. But the important thing is what you're looking at there is effectively the inrush, that we call this the inrush of the machine, where the current is very high. Now, one thing we said about this is if I look at the current should look 60 hertz-ish. And it does. But if I zoom in on it here, I see that it's 60 hertz plus some ripple. All right. What's causing the ripple? What's causing the ripple? What's that? Well, so we're driving this thing not with a pure voltage source, a pure cosine, right? We're driving it with that PWM wave, right? And that PWM waveform has a 60 hertz low frequency term, but it also has what? Has that high frequency stuff that I'm using, right? This is basically the result of that high frequency. If I don't like that, what should I do? Right? Well, the motor we said was kind of low pass filtery, right? Right, we said it had that nice low pass filter characteristic. Let's say what it's saying is my voltage has got a lot of high frequency harmonics in it. I want my current to not have those high frequency harmonics. What should I do? Add more inductance. So very often what you do is you put inductance in series with the motor, right, to sort of filter that down if you don't like it, right? And the other thing is you pick motors that are called quote unquote inverter duty motors. Right? If you take a regular motor, it's not designed to have that ripple in it. But you'll see motors that say they're quote inverter duty, and those motors are rated to be able to handle those higher frequency currents. All right, that's the basic procedure for you guys to sort of deal with looking at problem 1 and 2. All right, you can bet for sure that on exam that sort of exam 3 or exam 2. What do you expect to be there? You're going to expect to see an induction motor, a synchronous generator, and a DC machine, right? So this is the type of problem that I would expect you to see, except I'm not going to ask you to find probably the operating speed. I'll probably say, well, it's operating at whatever slip or whatever, right? And you guys will figure that out. Okay. All right.